We're going to discuss about a NumPy library on a random. So a random is a functions in NumPy library which generates a random number. You can generate random number in the forms of float or integer, and in the NumPy library we have functions available to generate a random number in an array. So let's see that what is a random number in the NumPy. The random number in a NumPy is generating an array, and whenever you run the program, the array will have a different value every time you run it. So the prediction is very logical, and it is not uh, constant every time you run the program. So we have two kinds of random number generation in NumPy. You have a pseudo random and a true random. So if there is a program to generate a random number, it can be predicted, thus it is called as a truly random. And a random number generated through a generation algorithm are called pseudo random. Now let's see that how you can run a random number and generate an array using a random number generation. So in the code, while you write, you can use to from the NumPy, that is you are importing from the NumPy an object called random, and in that object called random you have a function called ranInt, and then you define how much should be the size of the number to be generated. So let's run this code in a PyCharm and let's find out how it works. Now I have that code already here, that from the NumPy import the random, and the x is equal to the random int 100, and then print this x, and then we'll come to know. Let's run this code, and then you can see here the random number is generated as 52. If you give any number you want to generate it with an array, you can have a define as ranges. Okay, so right now we are going to see that how a random number is generated. So every time I run, you can have different number, but the number is between 100. It is not greater than 100, but every time you run the code you get a different number. Now let's see that how a random number can be generated by not applying any limit. So let's go to the code and say delete this 100 and run. What happens? It doesn't run anything, so this is an error. This shows what it's doing here. There should be at least one argument to be passed in the random. So if I say 1, then what will be the random number generation? It will generate either 0, or next time it is always 0 but not 1. So if I say 2, and then the random number will be either 0 or maybe 1, maybe 0, maybe 1, maybe 0, maybe 1. So it is alternately can be switched between that number by giving a limit to 2. So this is how you can also predict your output. Let's see that if I give a random integer generations by giving a 2 parameter, say 100, and with a size which is equal to 5, what happened to my array? So let's see in the PyCharm that I give a size of a limit of 100, and then I say the size equal to 5. Then what happened? Let's run, and then see here it generate a size of 5 number, which is totally a random between 0 to 100. So let me run once again. It's of difference but the size here. You can increase the size to 10 and see that how much is generated. It generated 10 number from the generation. Now let's see the next one conditions, that if I give a size of say 3 and 5, what happens to the code? So now if I give a size equal to say 2 comma 10 and close a bracket and run the code, let's see, it generates a 10 of 2 rows of 10 columns. You get a two-dimensional array. A two-dimensional array is generated. Okay, let's go and see the next way of generating a random. Here, the random number can be generated from an array, from any array, and by using choice. So here, the choice is a function which accepts a parameter called array, and here 3, 5, 7, and 9 is the number which is going to be occur in your array X. So let's see that how these functions work. Now in these functions, I will copy this line and then let me comment this line for future reference, and instead of random I will use choice. And when you give a choice, you define an array, and in the array I say 5. Okay, it's like 3, 4, 7, sorry, 7, 8. Now if what is the number will be appear. Let's run this code and see that occur is from the from this ranges a random number is generated by using choice. So you define already what should be your choice. Now in this choice parameter you can also generate a random distributions. A random distribution is a set of number that the probability density functions is also follows a random number, and then the probability can be defined of how probable or the occurrence of that particular number in your data sets. So if I give a choice with a with what is the number to be the range, and then you provided a probability of occurrence, then and you give a size of 100, then what happens to your x, to your array? And what is the probability of occurrence of 3 is 0.1. That means out of 10 it is like 10%, and the occurrence of 5 is like 3%, and occurrence of no I mean 30%, and occurrence of 7 is 60%, and occurrence of 9 is 0%. Means in that set of number that generated in an array called x with a size of 100, the occurrence of 9 is totally 0. That means 9 will never appear in this array. Let's see how it works. Now if I define a probability p equal to I will set an array of say 0.1 for the 3, and 0.3 for 4, and 0.5 for 7, and then 0.0 for this 8. Then I give a size. So in this size for small I'll just generate 10, and let's see how much it generate. I made a mistake. Probability do not sum to 1. So therefore I need to change this. If I change, instead of 6, if I put 0.5, and instead of 0 I put 1, and at least how much time the 3 appear, the 8 also will appear. Let's see that. See here, 8 appear 3 times, but 3 is not appear. Why? Because the probability of 3 and the 8 is same, So the number has been selected 8 more times than compared to 3. Now slightly if I change, I will reduce this to 4 and let me put 3 to 2, and let's run this code once again, and then the occurrence of 3 has came 3 times, but the occurrence of 8 is reduced. So because 8 is the least probability to occur in this. So if I change this size to 20, that means all the number will be generated or not. Let's see that. The random number generates at least one time in the occurrence of 8. So 8 comes at least one time in this number generation. So this is how you can choose with the probabilities and size and defined your number to be generated in an array. Let's see next example, a random permutations. Okay, so random permutation is nothing but you are giving a permutation combinations of occurrence of your number and arrangement of those element within your array. And here you can use two method. One is shuffle and one function is called permutation. Let's see the example. In example, I will be showing you a random number generation will generate an array of a NumPy array. In a NumPy array, you just shuffle the array, and let's see that how the NumPy array shuffles. Let's see in the code. So since we have an here, so what I will do is I will put an import NumPy as NP for example, and then we'll generate an array called arr equal to np dot array and define your array within this range. So I will select this array size and will have a shuffling. So random dot shuffle and give the array. Okay, after shuffling your array, you can print the array. Let's see what exactly it prints. Let's run the code and let's see that. See here 3487. So there is a shuffling between this number in this array. So shuffle is also one way of permutations of appearing. Now let's see that what is permutation. The same thing we can use permutation instead of shuffling. Now let's do another here, random dot permutation of the array, and then you print the array once again, and let's see that how it appears. Now here the shuffling and the permutations appear to be same. So here we are able to generate the then first I shuffle, and from the shuffle I use permutation. Now the same thing you can use it random dot permutation or random dot shuffle, the output remains same. Now in the Python we can visualize the output into a distribution visualizations, and in order to do that we used we use a library called Seaborn, and Seaborn is a visualization distributions in the NumPy. So in order to install Seaborn, you can use pip install Seaborn in case if you're using command prompt. Otherwise you can also add the packages in the PyCharm. So let's see that. Let's go to the package and type seaborn. Now you have a seaborn here, and you have to install the seaborn, and click here and install seaborn. When you add this package into this particular code, only will be receiving seaborn. So if you change this project, you need to add these packages every time in your code. Let's wait for a few minutes for the seaborn to add into this project. You can see that the seaborn package is installed successfully. Now, for example, we want to plot any graph from an array. You can use the distribution plot, or you can use those distribution plot in a matplot library, or you can import as a seaborn. Now, let's go and see an example using a matplot library as well as a seaborn. Now you have to import matplot library. Matplot library, you can see here, dot python plot as plt. This is matplot library is to show the visualization in a window. Then I need to import seaborn as, say, SNS, and this will do the distribution for plotting. Now before plotting, we need to have an array to plot. So let me consider this array as an array, and then you can distribute using a distribution plot. So as an example, you can see that the first we are going to use a distribution plot of that particular array. So I want to use SNS dot distribution plot of this array, and then I want to show the plot in the matplot library. So plt dot, you can use show, and just run this code. We'll see what exactly come. Okay, it's not able to generate. So guys, the problem of not able to generate the graph was we have to do one setting called for scientific tools. So when you come to tool setting, okay, in the settings, when you come to tool settings, there is one Python scientific. When you go inside this show plot tool window, make sure that it is not checked. Okay, it should uncheck, and then after that, if you are going to run this code which we have already made a distribution plot of that particular array, okay, and then I use for block true, and the interactive method is also false, then you run this code, you will be able to see the output. So this output, what you are seeing here, it is a seaborn output where you are seeing a histogram of here the distribution. So this is a distribution plot where you are able to see a histogram distribution between this range. So this is the range where you are seeing a density of the plot. So it is here, you can just see, if I go around and move around this plot, you can see the xy value of the plot value, where it is been on this surface. Wherever you move, you can see that. Okay, so this is the density, and this is not given into the plot. You can also define the leveling, you can also give the level. So here you can say where do you want to put the level. So there are ways of putting level in the x as well as y, and you can set your own leveling also. Let's go and see the next example of the distribution. Now using the distribution where we see a histogram in the center. If you don't want that distribution, you can you want to remove the histogram, you can still remove the histogram. And here in the SN distribution plot generation time, you can make this false. So I'm just going to copy this and we'll paste it here. So with this array, and here this is a histogram false, then if you run this code once again, you will be seeing that there is no histogram available in this range. So this is how the SNS, the C bone plot, can be shown for distribution plot. Now next example is about a normal Gaussian distribution. For a normal Gaussian distributions, you can see that there is three parameters required, where there is a mean, that is called LOC, and you should define a standard deviation and the size of the returning array. Let's go and see the example. So for example, let's generate a Gaussian normal distribution using random dot normal of size, and this is what we are going to generate an array called X. And then in the next one, we will be giving the LOC equal to 1, scale equal to 2, and then size of given as 2 by 3. So now here you are going to generate a matrix that is an array of 2 rows with 3 columns of random number. Now let's go and see that we want to generate a random array here. So what I'll do here is, let me comment this, and I will change array equal to, let's say, random dot random integer, say size equal to 2 comma 3. This SN will be used, also use normal, and for distribution we are going to use as distribution. For visualization purpose also we will be using as a normal distribution. So let's go and see that by changing this. So this is what you are seeing is a normal distribution graph representation. Now if I change this array, I will create an array with LOC. So here I will generate a random dot normal, and then you give an LOC equal to 1, then the scale, okay, equal to 2, and then I want to give size of the array equal to, say, 2 by 3, and then we'll generate this array. Let's see that how it works. Let me stop this and then we'll run once again. Okay, so this is how the distribution of this value, which has been a normal distribution points for the array, and this array has been used to plot here. Okay, so this is about the normal distributions, and visualization of normal distribution has been done. And then we have a binomial distribution. For binomial distribution, the same as you have to give three parameters. One is the n number of binomial, and p is the probability, and size s is the for the array size. So when you generate a random number, you will be using binomial instead of normal. So here you will be using as binomial, dot binomial, and then in here in the LOC you will be giving as n equal to 10, p equal to 0.5, and size equal to 10. This is what you are going to give here. So n equal to 10, and p, the probability p, say what is the probability, so 0.5 probability, and the size of the matrix is 10. Then let's see how this plot will happen using a distribution plot. Run this code, and this is how the distributions of binomial. Let's go and see next binomial distribution has been done using, you can have a histogram and you can have different parameters called KDE for binomial distributions, and still you can generate a code. Here we want to know what is the difference between a normal and a binomial distribution. The main difference between a binomial and the normal distribution is like continuous and discrete. So where you can have a normal distribution is a continuous distribution of the value, and as well as a binomial is a discrete value. So if I run a different binomial as well as the plot for both, you can see the comparisons of how the plot will appear into a single graph. So let's go and see the code here, that how it works. Okay, let me stop this, and before this let me have to run another array 1, and here I'll be calling as random dot normal, and you give an LOC equal to 1, and then you give a scale of 2, and then you give a size of say 2 by 3, and then I have a binomial distribution of random this size. Okay, so here is giving a same size so that your distributions will remain same. So here instead of 2 by 3 I will give as 10, maybe say 100. Here I will give 100 points, and then I will be generating two plot. So here I will put histogram true, and then the same SN plot will be generating for one. Then first is a normal and second one is for the binomial. So if I run this code, what happens, let's see the output. Now you can see here the plot of a different color is a binomial distribution, and this is a normal distributions. So you can compare that one of them is a very continuous and one of them is a discrete way of representing the code, the distribution. Now let's see what is a Poisson distribution. In the Poisson distribution, you can see it is a discrete distribution. It accepts two parameters. One is the rate of probability and one is the size of the array. In order to generate that, you can use a Poisson with a parameter called lamp equal to 2, which is the probability of Poisson, and then a size of thousands. You can give another parameter where KD is equal to false, but not necessary. So what I'll do is, in here I'll comment this, and then I will have another array. So the array here, this lamp LAM will use the lambda value, so 0.1. This is probability of occurrence. So here for example I'm getting as an integer value called 2, so I'll just put 2, and this probability not required, and then you give a size of 100, and I don't need this graph as of now, and we'll run this graph. Okay, this is wrong because I have didn't change this one to Poisson. So let me change to Poisson, then probably it will run. Let's see that this is a Poisson distribution. So this is a Poisson distribution graph, you can see here very clear. Now let's see the next example of difference between a normal distribution and a Poisson distribution. So here the you can have a normal distribution of the same size of that, and the lamb and the LOC is kept same, but scale is not given. Scale will be available for normal, but Poisson scale will not be available. And for the uniform distribution, similarly, you can have a uniform keyword and use the uniform functions and give the size of the one, and then generate an array. And after that, you can just put those random distributed into a distribution plot, and you can see that output. Similarly, for logistic distributions, you have a 3 parameter LOC scale in the size of the array. By you giving this parameter, you can generate a random number, and from this random array, you can pass through a distribution plot using the seaborn, and you can see the output. You can also see the difference between a logistic and a normal distribution, how it appears. Multinomial also the same way, you will be able to see a number of possible outcome. What is your number of possible outcome? N. And then you give your probability outcome, and then you give your size. So this is how you can generate a multinomial ways of generating. Then after generation of multinomial, you can just put it into your SNS and you can see the output. Similarly, this is an exponential, and then you have a visualization for exponential using the seaborn, and then you have a chi-square distributions where you will be giving two parameters, one for the chi distribution and one is the size of the array, and you can generate a random array using this parameter of this value and the array size, and then you can plot it into using a distribution plot. And this is a Rayleigh distribution. In the Rayleigh distribution, so you can give a scale which is a standard deviation value, and then you have a size of the array, and this is how you generate a Rayleigh array. And from this array, you can just put it into a distribution plot and see in the C1. Okay, distribution. Here you can see the difference between of a chi-square and the Rayleigh distributions. You can provide the different values and see there. And then next is the Pareto. Pareto is a very interesting one, where you can generate a number using a Pareto within of a size. And the Pareto law says that it is a 80-20 distribution factor. The same way you can generate a 80-20 distribution of Pareto random array, and then you can put it into a distribution plot, and you can just see the output, which is a zip flow. In the zip flow, the same way, you have to give a distribution parameter A and the size of the array, and you can generate an array called X, and when you after generation of X, you can put it those generation into a distribution plot, and you can still see the output. So this is all about visualizations. And guys, thank you very much for watching this video, and I really appreciate. I hope you will like this, and if you need more examples, we'll do it in the next video. Thank you. Bye bye. Have a nice time.